This video is one of a series of videos going through the AQA A-level Chemistry Paper 3 linked to the multiple choice questions. I'll put these videos together to talk through how to arrive to the correct answer for all of the multiple choice questions, because when you go through mark schemes they will give you the answers, but there will be no explanation as to how to get there. I'm guessing if you're watching this video you're more than likely just looking for a specific answer or a couple of answers. So when I've uploaded this to YouTube, I've put in timestamps so you can navigate to the correct question. But otherwise, if you wanted to just go through a whole paper and go through each answer, feel free to watch the whole video. So question 5 we've got here: which compound has the highest boiling point? So you've got your propan-1-ol, propanol, propanone and methyl ethanoate there. So highest boiling point, they're all molecular, so you're working out which one's got the strongest intermolecular forces. So here you've got your OH group, so you're going to have hydrogen bonds between molecules. You've got a C double bond O there in propanol. That's a polar bond, so you're going to have dipole-dipole forces between the molecule. Again with propanone, you're going to have a C double bond O, that's a polar group, so you're going to have the dipole-dipole group. And finally with the ester, C double bond O, single bond O there, that's your ester group. That is also polar, so you'll have dipole-dipole forces between molecules. As you should be aware, hydrogen bonds are stronger than dipole-dipole forces, so propan-1-ol would have the highest boiling point. For question number 6, we're looking at the melting points of the period 3 elements. So this is from the periodicity topic. These are all molecular structures apart from argon, which is monatomic. So you may remember the graph. You've got your period 3 metals, you've got silicon, which is macromolecular, and then you get down to phosphorus, sulfur, chlorine and argon with their melting points in Kelvin or degrees Celsius, doesn't matter. So phosphorus exists as P4, sulfur exists as S8, chlorine exists as Cl2, and argon again is monatomic there. They are all molecular apart from argon, and therefore we're just focusing on the van der Waals forces between molecules or between atoms of argon. Sulfur is the biggest of the 4 substances there, phosphorus is the second biggest, then chlorine, and then argon exists as single atoms. So because sulfur is the biggest molecule, it's got the strongest van der Waals forces between molecules. That means S8 followed by P4 followed by Cl2 followed by Ar, which gives us answer C. So question 7, which is not a correct statement. So in these sorts of questions you want to read through each statement, eliminate the ones that you know are correct. So transition metals form coloured ions and complexes. Hopefully you're aware that of some examples of transition metal ions, so like your dichromate ion or your chromium 3+, orange and green, manganate, which is a transition metal ion, purple. Complexes like your hexa aqua copper ones, which are blue. So yes, they do exist as various coloured ions and complexes. That's a correct statement. Statement B. Transition metals display variable oxidation states. So things like Fe, which you should be aware of exists as Fe2+, Fe3+. The dichromate, which I mentioned before, dichromate has a +6 oxidation state, whereas chromium 3+ is 3+. So yes, they do exist as variable oxidation states. Statement C. A ligand accepts a pair of electrons from a transition metal. Accepts a pair of... That doesn't quite sound right. With these sort of questions you do want to read all of them just to make sure that you've checked over. So let's go back to statement C in a second. Statement D. A complex is a central metal atom or ion surrounded by ligands. So your transition metal will form coordinate bonds, often 6 coordinate bonds, with ligands such as water, it could be hydroxide, could be ammonia, chloride, etc. So that is a complex. so that's correct. So going back to statement C, a ligand accepts a pair of electrons from a transition metal. So your ligands, again such as water or ammonia, has a lone pair of electrons. Transition metal ion, positive. A ligand will therefore donate a pair of electrons to the transition metal ion. So that statement is incorrect because it says a ligand accepts a pair. Statement C is incorrect, so answer C is correct. Question number 8. The table shows possible conditions and products for the cracking of alkanes. So you do need to know two different types of alkanes, which we can see in this table here. There is thermal cracking and there is catalytic cracking. So this is just some information that you do have to learn. So thermal cracking, the conditions for this is high temperature, high pressure, and thermal cracking will produce mainly alkenes and shorter alkanes. Catalytic cracking is carried out under slight or moderate pressure and a high temperature. And the name says catalytic, so that suggests a catalyst. A zeolite catalyst is often used. So there are your conditions. Catalytic cracking will often produce branched alkanes, cyclic alkanes, or benzene compounds or aromatic compounds. So that's the information on cracking. Let's just go through the table. Let's see which one matches up these bits of information here. So thermal, carried out high pressure, high temperature, that's correct, but it doesn't produce mainly alkanes, it produces mainly alkenes. Statement B, or row B, thermal cracking does produce mainly alkenes. It's carried out under high pressure, but it's also carried out under a high pressure. Statement C, catalytic, carried out under slight pressure and high temperature. So slight pressure, high temperature. It produces mainly branched alkanes and aromatic. So we can see statement C looks like it's correct. Just double check statement or row D. Row D is incorrect because it's not carried out under high pressure. So answer C is correct there. Question number 9 then. Trichlorophenol is a weak monoprotic acid. Gives you the Ka value there. And it's asking you to calculate the concentration of H plus ions in a 0.002 mole per decimeter cube solution of the trichlorophenol. So it is a weak acid. So the first thing you're being asked to do a calculation with a weak acid, you should be thinking to do the Ka expression. So Ka is your H plus concentration times by the concentration of the salt. We'll just write A minus divided by the concentration of the acid, the trichlorophenol, which will give as HA. The formula of trichlorophenol is not going to help us here, so it doesn't matter. We can just use the general expression for a weak acid. So because it's a weak acids dissociate or partially dissociate to give H plus and A minus ions. The assumption we can make if it's just a weak acid, which it is in this question, is that H plus equals A minus. And again, this allows us to simplify the Ka expression make it easier to solve using the H plus squared, because H plus equals A minus, we no longer have to times those together, H plus squared over HA. So we can use this assumption anytime there's a weak acid calculation and there's no other chemicals present. It's asking us to calculate the concentration of hydrogen ions, or H plus. So we need to rearrange the Ka expression to make H plus the subject. So to make H plus the subject, I'd multiply both sides by the HA, so Ka times HA, to give me H plus squared, so times that across, and to get H plus on its own, I'm going to square root both sides there. So square root Ka times HA equals H plus. It's good practice to just put things in brackets on your calculators just so you're not messing up the numbers or the instructions you're putting in there. So I'd often just put the square roots on the outside of a set of brackets there. So the h plus, let's just have a look at the numbers in the question, can be calculated by doing the square root of Ka, which you can see at the top of the screen there, 2.51 times 10 to the minus 8, times by HA concentration, or the acid concentration, which is this one here, 2 times 10 to the minus 3, or 0.002. Plug that into your calculator, square root your answer, and that should give you a final answer there of 7.09 times 10 to the minus 6. Let's just check through the answers, hopefully it's there, and we can see it is answer B. Question number 10, also from the pH topic. What is the pH of 0.46 molar potassium hydroxide at 298 Kelvin? And the reason it's telling you that is because we have hydroxide, which is a base, and to calculate the pH of bases, we will use the Kw value, which it gives you there, 1 times 10 to the minus 14 at 298 Kelvin. So potassium hydroxide, KOH, is a strong base. It will fully dissociate into K plus and OH minus ions. You can also see the ratio in this equation of KOH, potassium hydroxide, to hydroxide being a 1-to-1 ratio. So if it's a 1-to-1 ratio, whatever the concentration of potassium hydroxide is, in this case 0.46 moles per decimeter cubed, will produce the same concentration of hydroxide ions, 0.46 moles per decimeter cubed. So if you know the concentration of hydroxide, how do you work out the pH? And again, you need to use the Kw expression here. So Kw is the concentration of hydrogen ions times by the concentration of hydroxide ions. If you know H+, you can work out pH. So let's find H+ then, because we have OH- and we have Kw. H+ equals Kw then divided by hydroxide concentration, or 1 times 10 to the minus 14 divided by the concentration of OH-, which is 0.46. And that gives us a hydrogen ion concentration of 2.1739 times 10 to the minus 14 moles per decimeter cubed. What is the pH of this? Well, you've got the H+ concentration. So if you minus log the H+ concentration, minus log your answer, you should get the pH. Remember, it's a strong base, so you're looking for a relatively high pH, and that gives us an answer of 13.66. Answer B. So here we have question 11, chemical calculations topic. What's the mass in milligrams of carbon formed when 3 times 10 to the minus 3 moles of propene undergoes complete combustion? So we're trying to find the mass of carbon there, and we're given the moles of propene. So firstly, if you know the moles of your reactant, you can work out the moles of any other chemical in the equation using the stoichiometric or the balanced equation ratio. So we've got a 2-to-6 ratio there. So if you've got 0.003 moles of propene, C3H6, that means we're going to have to multiply that by 3, 2-to-6 or a 1-to-3 ratio, to work out the moles of carbon. So 0.003 times by 3 gives us 9 times 10 to the minus 3 moles. Now that we know the moles of carbon, we're being asked to calculate the mass of carbon in milligrams, which we'll get to after. So the mass of carbon is the moles times by the atomic mass of carbon, so 0.009 moles times by 12, which gives us a mass of 0.108 grams. How do you get from grams to milligrams? Well, 1 gram equals 1,000 milligrams. So 0.108 grams, need to times it by 1,000, will give us 108 milligrams, or 1.08 times 10 to the positive 2. Answer C. Question 12, infrared. For this question, hopefully you're aware, but you will need to use the data sheet, table A or table 1. So on this, we'll just be focusing on the peaks to the left of around 1500, so that's your fingerprint region, so we can ignore the things over to the right hand side. So we've got two main peaks to look at. We've got one at around 1700, which could be an alkene. It's quite sharp and quite long, so it's much more likely to be a C double bond O peak. Let's just check through the answers there. None of those are alkenes, so it wouldn't be a C double bond C. So the peak at 1700, or approximately 1700, is due to the C double bond O. So that rules out butan 1-ol and bromobutane. Both butanal, which has C double bond OH, and butanoic acid have a C double bond O, so it could be answer C or D. Butanoic acid would also have a very broad peak for OH acids. We can see that peak is missing, so it is not a carboxylic acid. This little peak here is responsible. The CH bond is responsible for this peak. So there is no OH acids peak, so it can't be butanoic acid. It has to be butanal. So answer C is correct for that one. Question number 13. Which of these compounds does not form a racemic mixture when the compounds are reacted together? So remember, a racemic mixture is where you have optical isomers or enantiomers at an equal molar ratio. So you've got 1:1 or 50-50 mixture of both of the optical isomers. So going through each of the reactions, obviously we're going to have to work out the products. So if you react an alkene with HCl, you're going to get a chloroalkane in this case, and you'll get 2-chlorobutane. So that will be CH3, CHCl, CH2, and CH3 there. So A produces 2-chlorobutane. B, you're reacting an aldehyde with hydrogen cyanide, so you're going to get a hydroxynitrile, so you've got 1, 2, 3 carbons there, CH3, CH2, the C double bond O becomes OH, and a CN joins on there. So that's compound B. Compound C, you're going to have your butanone reacting with HCl. The H is going to join on the end because it forms a more stable carbocation, and the Cl is going to join on carbon 2 there. So your H of HCl, H there, Cl there. You're going to actually get the same compound as A. And then finally we have propanone. That's reacting with HCN, so once again you're going to get a hydroxynitrile with the formula there, because the C double bond O is in the middle. So alkenes and carbonyl compounds have a planar group that is attacked by the electrophile in the case of the alkene, or attacked by the nucleophile in the case of the aldehyde or ketone. So because these are planar, the electrophile or the nucleophile is going to attack either above or below the plane with equal probability. So if the product has a chiral carbon, you are going to get a racemic mixture formed. because the double bond makes the group planar, so the adjoining species again will attack with equal probability. So let's just go through all of the answers again. A again is 2-chlorobutane. You can see the second carbon is chiral. It exists as optical isomers. It does form a racemic mixture. C formed the same product, so C will also form a racemic mixture. The cyanide attacks equal probability above or below the plane. So the two different optical isomers are going to exist because this compound here, you can see the second carbon has 4 different groups attached. Chiral carbon, optical isomers, and it would be a racemic mixture. D is a symmetrical ketone. It's got 2 CH3 groups on there, so you could possibly work it out without having to work out all the products, but you can see clearly there's no chiral carbon because there's 2 of the same group on this carbon here. If there's no chiral carbon, there's no optical isomers, it can't be a racemic mixture. So C would not form a racemic mixture, meaning D is correct. Question 14. Reaction sequence shows how ethane CH3CH3 can be converted into 1,2-dibromoethane after step D. Which step occurs by nucleophilic substitution? So you can work out what each step is, or you can just understand how nucleophilic substitution occurs. So I'll talk through both very briefly. So nucleophilic substitution occurs with haloalkanes, where the halogen is substituted out for a hydroxide ion or for an ammonia molecule to form an amine, or from a cyanide. So you can just have a look there, see which one's happening, but I'll just talk you through, just eliminate the other steps, just in case you weren't sure of it. So you're going from an alkane to a haloalkane in step A. Halogen is used. The CC bonds and the CH bonds are fairly inert, so this will only occur in the presence of UV light. So step A is free radical substitution. Step B, we have a haloalkane and we're going to an alcohol. This will happen provided the sodium hydroxide is dissolved in water. If it's an aqueous solution. So this one, the OH substitutes for the chloride, the hydroxide ion acts as a nucleophile. So step B is nucleophilic substitution. If you weren't sure about this between the other answers, let's just check step C. Step C, you have an alcohol and you're going to an alkene using concentrated sulfuric acid. So you're removing a water molecule, you're dehydrating it, or elimination is occurring in step C. And finally step D, you're going from an alkene, adding a halogen, double bond breaks, and you're getting a bromine atom on each side of the double bond. That is electrophilic addition, which we saw in question 13. Question 15. Cisplatin is an anti-cancer drug. Which structure represents a stereoisomer of cisplatin? So cisplatin, you should know, is platinum with 2 chloride ligands and 2 ammonia ligands. It's cisplatin because the 2 NH3s are next to each other and the 2 chlorides are next to each other. Cis is a little bit like Z isomers in the fact that they're on the same side, they're next to each other. You've come across cisplatin in the biochemistry topic because it's an anti-cancer drug. It binds to the guanine on DNA. Transplatin then, the stereoisomer, is going to have your platinum with your Cls on opposite sides and your NH3s on opposite sides. So let's just look at the options given to us here. It can't be C or D because they have NH2s, not NH3s. It's an NH3 ligand rather than an amine group. You then have A and B. A is cis because the chlorides are next to each other. B is trans because the chlorides are opposite each other. That's what trans isomer means. So B is correct. Question 16, we've got something different. We're looking at the Maxwell-Boltzmann distribution. We've got 4 letters. Which letter represents the most probable energy? So because we've got letters on the x-axis, we've got 2 letters on the y-axis. It will help to label those axes. So in a Maxwell-Boltzmann distribution, you have energy on the x-axis and you have number of molecules on the y-axis. So most probable energy, it's not going to be on the y-axis because you're looking at number of molecules. So that rules out A and B. So which one is the most probable energy at a higher temperature? So most probable energy is the peak of the curve, or the highest energy, the most probable energy. So these are the most probable energies. Which one is the peak at a higher temperature? So at a higher temperature, the peak will get lower and shift to the right. You see more molecules have the activation energy or greater, or many more molecules. So this curve here, I'm attempting to draw around, is the one at a higher temperature, and therefore D is correct. That's the most probable energy. So question 17, vanadium can be used in the contact process as a catalyst. This is from the transition metal topic. Which is a step in the contact process in which vanadium is oxidized? So this is one of those that you do need to learn. The contact process is the production of sulfur trioxide, SO3, from sulfur dioxide and oxygen. V2O5 is our catalyst here. So what happens in this reaction? Your V2O5, again this is just a couple of equations you have to learn, V2O5 will react with SO2 to produce SO3. We then get an intermediate formed, which is VO2. The intermediate, VO2, will then react with oxygen to form V2O5. It regenerates our catalyst. Our intermediate gets used up. The catalyst, used up in the first step, regenerated in the second step. Overall equation, we can see there, SO2 plus half O2 makes SO3. Which one is showing the vanadium being oxidized then? So what's the oxidation state when it's V2O5? Each oxygen is -2, so that gives us -10. That means the vanadium must be +5 here. So you've got 2 vanadiums. What's the oxidation state in VO2? Well, oxygen's -2, so you've got 2 lots of -2, so the vanadium must be +4. So when V2O5 goes to VO2, going from a +5 to a +4 oxidation state, the vanadium is reduced. So V2O5 to VO2 cannot be correct. Where the vanadium is oxidized, it's going from +4 in the second step to +5. So VO2 back to V2O5 is going to be an oxidation process. So which one of these 2 equations is correct? Step B. Step B is incorrect because you're going from SO3 to SO2. That doesn't happen in the contact process. We're going from SO2 to SO3. So B is incorrect. Let's just check C. VO2 plus half O2 gives off V2O5. So that's that equation there. The second step in the contact process, showing how the catalyst works. So C is correct. Question number 18. This structure shows a section of a polymer chain formed from the random polymerization of 2 different monomers. Which pair of monomers could produce this polymer? So we've got a pair of monomers. It's showing carbon-carbon bonds. There's no COs, no NH groups. So this is addition polymer. So we're trying to work out which alkenes were present, and you can see there's alkenes in the answers. So you're trying to work out how it's arranged so you can find the repeating pattern. So going through, you might have the split here, so you might have a C11C with a CF3. You've got 2 carbons there, so you've got an F and 3 H's. Let's just see if I split it here, what have I got? I've got 3 H's and an F again. I've got 3 H's and a CF3 again. So you might start to see the repeats from just splitting 2 carbons at a time. Where's the double bond in the alkene? I can see that one of them has a fluorine on the alkene and one of them has a CF3 on the alkene. So which one does that look like? I think it's going to be A. Let me just skim through those. That's an ethene, which isn't there. It's not going to be that one, so A is the correct answer in this case. Question number 19. In this reaction between zinc and hydrochloric acid, here's your equation. What's the minimum mass in milligrams of zinc needed to react with this volume and this concentration of hydrochloric acid? So to work out the mass of zinc, we need to obviously know what the moles of HCl is. How do we work out the moles of HCl? Moles of HCl is worked out by doing concentration times volume. So we've got the concentration being 1.68 and we've got the volume being 50 centimeters cubed. So don't forget to divide that by 1000. So the moles of HCl there is 0.084. Once you know the moles of one thing, you need to work out the moles of the other thing using the balanced equation ratio. So the moles of zinc, using the equation and the ratio, is going to be the moles of HCl divided by 2. So 0.084 divided by 2, it's going to be 0.042 moles there. What's the mass in zinc? In milligrams, sorry, of zinc? It's going to be your moles times by your AR. So moles of zinc times by the atomic mass of zinc. That's 0.042 times by 65.4, and that gives us a mass in grams, remember, of 2.746 grams. That's grams. 1 gram is 1000 milligrams. 2.746 grams is going to be 2746 milligrams, which is this answer here. Question number 20. We've got an equilibrium question. We've got this equilibrium mixture here. Temperature is decreased. What's greater for the new equilibrium than for the original equilibrium? So it's saying which is greater. So you are going to have to go through process of elimination, work out what's happening. So the temperature of this mixture is decreased. So if the temperature is decreased, the forward reaction is exothermic. So if the temperature drops, equilibrium is going to shift this way. It's going to produce more COCl2 and less carbon monoxide and chlorine. So what's going to be greater? Well, the mole fraction of carbon monoxide is going to be less because equilibrium is shifting to the right. So that's going to be less. Partial pressure of chlorine. Well, if you're making less moles of CO and less moles of Cl2, the mole fraction of both carbon monoxide and chlorine are going down, as are the partial pressures. What's going to happen to the total pressure? Equilibrium is going to shift to the side with fewer moles of gas because it's moving this way as the temperature is decreased. So the total pressure of the mixture is going to go down as well. The value of the equilibrium constant. Now remember, equilibrium constants Kp or Kc are affected by temperature. If the forward reaction is exothermic, which it is in this case, increase in temperature will cause Kc or Kp to decrease. A decrease in temperature is going to cause Kp or Kc to increase. So if we decrease the temperature, which one is greater? The value of the equilibrium constant is going to increase. So D is correct there. Question 21. This is a novel mechanism, one that you won't have come across before necessarily. So it's saying which arrow does not appear in the mechanism. So even though it's not a mechanism you're expected to know specifically, you have to just sort of work out what's going on here. So you're going from a C double bond O to a C double bond C and a single bond O. So C double bond O going to a single bond O, you've seen that in nucleophilic addition and addition elimination. So your double bond O goes to a single bond O there. So D is a correct arrow. We're going from a C single bond C to a C double bond C. So you've seen this in elimination, where your hydroxide attacks a CH or accepts a proton, and your C single bond C gains an extra pair of electrons to form the C double bond C. So that's what happens in elimination. This one happens in nucleophilic addition. So your hydroxide ion acts as a base, accepts a proton. That arrow is correct. A pair of electrons in the CH bond snap upwards to form a C double bond C. So that also happens. The electrons don't come down here. You've not come across any arrows like that in any of the mechanisms you've learnt. So this one is not going to appear in the mechanism. Question 22. Diagram shows a pH curve produced by adding a strong alkali, such as sodium hydroxide, to a weak acid. So organic acids, ethanoic acid for example, it doesn't matter. Which point on the curve represents a solution that can act as a buffer? So remember, a buffer is something which resists change in pH despite the addition of acid or alkali in small quantities. So a buffer is also made up of a weak acid and its salt. So which portion of this curve are we going to have a weak acid and its salt? It can't be A, because that's just going to be the weak acid on its own. C, it is completely neutral, that's your equivalence point. And D, you've got the hydroxide in excess. Stage B, this is the buffer region. Notice the pH is barely changing, so it's resisting changes in pH. Some of the acid has been reacted, but you've still got lots of the acid in excess. And the hydroxide reacts with the acid to make some of the salt. So B is the correct point, and this is known as the buffer region on a pH curve. Question 23. Which one could not be produced by the reduction of an aldehyde or ketone? So remember, ketones can be reduced to secondary alcohols. Aldehydes can be reduced to primary alcohols. So going through each one of these, if you're not sure, it might be worth drawing them out. 2,2-dimethyl propan-1-ol. So you've got 3 carbons in a row. You've got your methyl groups on carbon 2, and you've got your OH on this carbon here. That's a primary alcohol. So that would be formed by the reduction of an aldehyde. 2-methyl butan-2-ol. So you've got 4 carbons, you've got a methyl group on carbon 2 and an OH group on carbon 2. This is a tertiary alcohol, so it can't be formed by the reduction of an aldehyde or ketone. Let's just check the other ones. Butan-2-ol, so you've got your OH on carbon 2 and your methyl group on carbon 3. That one's secondary, be formed from a ketone. And pentan-3-ol is going to be a secondary alcohol as well. So the tertiary alcohol can't be formed by the reduction of an aldehyde or ketone. Question 24. Which one does not show stereoisomerism? two types of stereoisomerism. You have optical isomerism, and you have geometric or EZ isomerism. So first things first, let's draw out the molecules, work out what we have. So you have dichloropropene with 1, 2, so you've got chlorine on carbon 1, chlorine on carbon 2. That leaves us with an H there, that's for A. B, we have 1, 2 dichloropropane. So you've got your Cl there, you've got your Cl there. And your CH3. C, we've got 1, 3 dichloropropene. So you've got your C to 1C. You've got your CH3, your Cl on carbon 3. And your Cl on carbon 1 there. And D, we have 1, 3 dichloropropane. So you've got your CH2Cl, CH2, CH2Cl. So which one does not show stereoisomerism? So A would show EZ, because you have two different groups on each side of the double bond. So that would show EZ, that would show stereoisomerism. C, you have two different groups on each side of the carbon in the double bond, so C will also show EZ isomerism. So A and C do show stereoisomerism, they're not the correct answers. These two, B and D, one of them will show optical isomerism, one of them will not. B, does it have a chiral carbon? This one's not chiral because it's got two hydrogens. Second carbon, has it got four different groups attached? 1, 2, 3. And this is a fourth group because it's not a CH3, it's a CH2Cl. So that does have optical isomerism. So hopefully D does not have optical isomerism, and we can see there you've got two hydrogens on each of the carbons, so it definitely can't be chiral because there's not four different groups attached. So D is the correct answer there. Which compound can form a polymer without needing another reagent? So question 25. So polymers, they can form addition polymers if you have alkenes. None of those are addition polymers, or could form addition polymers because there's no alkene. Or you can have condensation polymers, which are formed between often diols or diamines and dicarboxylic acids or diacyl chlorides. So that will get you polyamides or polyesters, depending what's joining together. So in order for a single monomer to form a condensation polymer, it needs to have an OH or NH2 group and a COOH or a COCl group. It needs to have both of them in order to form the repeating unit or the polymer. This one, diol, wouldn't react with itself. Dicarboxylic acid wouldn't react with itself. This one has an acyl chloride and an alcohol group. Alcohol group and an acyl chloride, so it's probably that one. Let's just eliminate option D, which has a chloride and a carboxylic acid group, which isn't one of the answers. So C is correct there. Question 26. Solution of lead chloride, tells you the MR contains this mass of lead chloride in 100 centimeters cubed. It fully dissociates into its ions. What's the concentration of chloride's ions in this solution? So we've got a solution of lead chloride, and it's saying when the solid is dissolved, it's going to fully dissociate into its aqueous ions there. What's the concentration of chloride ions? So step 1, you've got your mass of lead chloride divided by the MR of lead chloride, which it kindly gives you, so you don't have to work that one out. So mass over mR in that case is going to give us the moles, which is 3.8 times 10 to the minus 3, 3.9 I should say, 0.00388 moles. That is in 100 centimeters cubed, so we can being asked to work out the concentration. So moles divided by volume, which is 100 centimeters cubed, or 100 over 1000 to give it decimeters cubed, gives us the concentration of lead chloride in solution. So that's 0.03882 mole per decimeter cubed. So if I've got 0.03882 moles per decimeter cubed of lead chloride, notice there's 2 chloride ions for every PbCl2. To find the concentration of chloride, I'm going to need to times that by 2. So that'll give me my final answer of 0.0776 moles per decimeter cubed, which is answer B. So on to question 27 then. So you're given the rate equation for an acid catalysed reaction between iodine and propanone, and you can see it's K times the hydrogen ion concentration times by propanone. It mentions iodine here, but it's not in the rate equation, which means that iodine must be 0 order, so it's not written in there. It gives you the original pH of the first reaction mixture. In a second mixture, the concentration of sulfuric acid was different, but the concentrations of iodine and propanone were unchanged. So we're only changing the acid concentration. The new rate of reaction was a quarter that of the original rate. What's the pH of the second mixture? So there's a couple of calculations to do here. First one is, okay, what's happening in this second mixture? The acid is changing. Remember, acid is H+. So your concentration of hydrogen ions is changing, but everything else is unchanged. The new rate of reaction was a quarter that of the original rate. So if the rate is decreasing by 4, and hydrogen ions are first order, or it's first order with respect to H+, the hydrogen ion concentration must also be quartered, or dividing by 4. So you're given the original pH. pH is 0.7. So what is the original hydrogen ion concentration? And hopefully you can remember how to work out the hydrogen ion concentration from the pH. 10 to the minus pH, or 10 to the minus 0.7, will give us the original hydrogen ion concentration. So our H+ concentration is 0.1995 moles per decimeter cubed. In the second mixture, the rate is a quarter, so what's happening to H+, because it's first order again, the hydrogen ion concentration must be divided by 4 as well. So 0.1995 divided by 4 will tell us the new hydrogen ion concentration. 0.4988 moles per decimeter cubed. So what's the pH of the second mixture? If you know the H+ concentration, you can find the pH by doing minus log of the H+ concentration. So minus log of 0.04988 gives us a final pH of 1.30, which links up with answer B there. Question 28. You're given volume of CO2, the pressure, temperature, and you're told the moles of argon and the gas constant. So this information should lead you to think, okay, I should be looking at the ideal gas equation. What's the mole fraction of carbon dioxide in the mixture? So what's the mole fraction of carbon dioxide? Well, we're not actually given the moles of carbon dioxide, so we can't yet work out the mole fraction. So you've got the pressure, you've got the volume of carbon dioxide, you've got the gas constant, and you've got the temperature of the mixture. So we can work out the moles of CO2. The moles of argon we don't need just yet. we need the moles of argon when we're working out the mole fraction. Remember, mole fractions comes from the KP topic. So how do you work out the moles of CO2? Well, you rearrange that equation there. So the moles of CO2 equals pressure times volume over R times T, the gas constant times by temperature. What's the pressure? Read the question, it's 100 kilopascals. Convert to SI units, that's 100,000 pascals. Times by the volume of carbon dioxide, that's 385 centimeters cubed. Converted to meters cubed, so you divide it by a million or 10 to the 6, or times 10 to the minus 6. So again, make sure your pressure and your volume are converted to SI units. Divided by R, gas constant, which is 8.31, it's given to you in the question, and the temperature of 25 degrees, don't forget that needs to be converted to Kelvin by adding 273. So we're working out the moles of CO2 here. The moles of CO2 can be calculated. Plug those numbers into your calculator, and that gives us 0.01554 moles. How do you work out the mole fraction? So the mole fraction of CO2 is the moles of CO2 divided by the total moles in the mixture, which is why we were told the moles of argon earlier. So the moles of CO2 is 0.1554 divided by the total moles in the mixture, which is the moles of CO2 plus the moles of argon, which we can get in the question, 2.89 times 10 to the minus 2, or 0.0289. Plug that into your calculator and you should get an answer of 0.3498. Hopefully that matches up with one of our answers above. Rounded to two significant figures, that's answer A. On to question 29. How many peaks does this compound have in its carbon-13 spectrum? So it may help to draw it out using structural formula or showing the actual carbons instead of skeletal formula. So I'll just quickly draw this in now. So you've got your double bond there, you've got a single bond to the S there, then you've got carbon, another double bond, single bond, another double bond, and that's a single bond to the last one. Hydrogens don't really matter, but I'll just add sticks to represent where the hydrogens would be. Because it's carbon NMR, we're just focused on the number of carbon environments. So in this structure then, what we have is a sulfur atom on the left ring. And because of that sulfur, that means the molecule's got zero symmetry. So let's just take this carbon to the left of the sulfur as an example. Why is that carbon not equivalent to any of the other carbons? Well, because it's got a sulfur one side, and then if I go this way round, got a double bond, single bond to the S. Let's just take one carbon from the other ring just to show that there is no symmetry. So why is this carbon not equivalent? Well, if I was to go this way, I'm going to have a double bond, then a single bond, then a single bond to a sulfur. If I was to go this way round, why is it not equivalent? There's no other carbons that will have the exact same pattern of carbons. So every carbon is in a different carbon environment. So how many carbons are there? How many carbons have I just circled? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 carbon environments due to the lack of symmetry. Question 30. Students provided with 5 centimeters cubed of 1 mole per decimeter cubed ammonia solution. The student was asked to prepare an ammonia solution with a concentration of 0.05 moles per decimeter cubed. So what volume of water should the student add? So you've got a concentration of 1 mole per decimeter cubed. How do you get from 1 mole per decimeter cubed to 0.05 moles per decimeter cubed? We have to divide it by 20. So one way you can work this out, how much volume needs to be added, is you can work out the moles of ammonia. So the moles of ammonia is concentration times volume. So concentration is 1, volume is 5 centimeters cubed. So that gives us a moles of ammonia being 0.005 or 5 times 10 to the minus 3. We want a new concentration of 0.05. So what volume of ammonia is needed in total? How do you work out volume? We do moles divided by concentration. So 0.005 moles divided by the total concentration of 0.05. So that gives us 0.1, remember that's decimeters cubed, or 100 centimeters cubed. What's the original volume? We've got 5 centimeters cubed of NH3 to begin with. We want to get the new concentration of 0.05. So we need a total volume of 100 centimeters cubed. So therefore we need to add 95 centimeters cubed to the original 5 centimeters cubed. So we need 95 centimeters cubed to be added to give us that concentration. Answer B is correct. Question 31. A solution absorbs light with wavelengths corresponding to red, yellow and green light. Which ion is most likely to be in the solution? So remember, transition metals or any solutions, light passes through them. Light of certain wavelengths will be absorbed. The light that is not absorbed is going to be passed through or transmitted and seen. So if it's absorbing red, yellow and green, the solution will not appear as red, yellow or a combination of those, or green. So let's just go through the ions that we're given. These are all ones on the specification, ones that you should have learned. So you've got the dichromate ion, which is orange. You've got the aqueous transition metal ions here. Just a quick reminder, aqueous transition metal ions are actually existing as the hexa aqua complexes. Excuse the terrible writing there. So Fe2 plus or hexa aqua ion 2 is green. Hexa aqua ion 3 is either violet or actually appears as a sort of orangey brown colour. And copper 2 plus, hexa aqua copper 2 is blue. So it can't be dichromate because that appears as orange, which means red and yellow light would be passing through, not being absorbed. So it's not dichromate. Green light is absorbed, so it can't be Fe2 plus. Similar to dichromate, the fact that Fe3 plus appears as orange-brown means red and yellow, or a combination of those wavelengths of light, will be absorbed. Because red, yellow and green are absorbed, blue is passing through. It doesn't mention blue in the question. You should know copper 2 is blue. So answer D is correct. Question 32. So you've got an exothermic reaction and a negative entropy change. Which statement is correct? So before I go through the statements, if you're told about the enthalpy and you're told about the entropy, you should be thinking about the equation for delta G there. So I'll just write that a little bit neater. So your Gibbs free energy change is your enthalpy change minus temperature times by delta S or entropy. So in this case, enthalpy change is exothermic, so delta H is negative. Temperature in Kelvin is always positive, and it's saying the delta S is a negative value. So temperature times by a negative value. So what you've got here then, the Gibbs free energy is your enthalpy, negative enthalpy, minus a negative answer because delta S is negative. For the reaction to be feasible, delta G must be negative in overall. So how do we make this reaction be feasible? Well, if you've got a minus
and you're subtracting another minus, you're essentially got a minus and a plus there. So whether delta G is positive or negative depends on the magnitude of delta S and the magnitude of delta H. Delta H is fixed, your enthalpy change doesn't change. So what would cause delta G to be negative? Delta G would be negative if your enthalpy change is more negative than T delta S. So the reaction is not always feasible. The reaction is not going to be negative. But the reaction is not always going to be positive either. So that rules out answer A and D. So what would cause the reaction to be feasible? Well, if the reaction is exothermic, what would cause the reaction to be more feasible? It's going to be more feasible if the temperature is reduced. You can kind of think, apply Le Chatelier's principle here if it was a reversible reaction. Remember, to get more products, if the forward reaction is exothermic, you make it cooler. Let me just show you with the delta G equation very quickly. So if you've got delta G with a fixed enthalpy value and you're minusing a small temperature and a negative delta S, so a negative value minus a small temperature would give you a negative answer overall. If you've got a bigger temperature, got a fixed value of delta H, but a big temperature, then you've got a minus value minus a bigger negative value, which will give you a positive answer. I.e., a higher temperature would make it less feasible. Delta G would be more positive at a higher temperature. Question 33. So we've got a yield question here. It gives you the balanced equation. You're told the mass of ethanoyl chloride, this substance on the left, is 5.7 times 10 to the minus 2 kilograms. 0.057 kilograms. Or let's turn that to grams, which is 57 grams. The percentage yield of phenylethanone, so that's this substance here, is 62%. So what mass was produced? So if you've got 57 grams of your reactant of ethanoyl chloride, tells you the MR of ethanoyl chloride, 78.5, you can work out the moles of ethanoyl chloride used. So 57 grams divided by the MR gives us 0.726 grams of ethanoyl chloride. Balanced equation is given. It's a 1-to-1 ratio there between our reactant and our product. So if every single molecule of ethanoyl chloride was converted to phenylethanone, the absolute maximum moles of product would also be 0.726 moles there. Moles, not grams, apologies. So 0.726 moles of our product is 100% of the yield. What's that if it was a mass? So what is the theoretical or the maximum mass of the product that we could make? So the maximum moles is 0.726 times by the MR. So you need to work out the MR of phenylethanone, which is 120. So 0.726 times by 120. I'll just write the formula for phenylethanone there so you can work that out if you need to. That's C6H5COCH3. So theoretical yield is moles times by MR, which gives us 87.12 grams. assuming every single molecule gets converted. That's 100%. The actual yield is 62%. So you need to work out 62% of our maximum yield, 62% of 87.12, or 87.12 times by 0.62 to give us 54.0 grams there. Hopefully that's one of the answers, and it is. It's answer B. Finally, question 34. So you've got a mixture, 130 centimetres cubed of oxygen, 40 centimetres cubed of nitrogen. Same temperature, same pressure, same volume. What's the pressure of the gas mixture in the flask at 298 Kelvin? So we're being asked to work out the total pressure there. So the pressure is originally 100 kilopascals. The volume is our original volume there, which is 130 plus 40, or 170 centimetres cubed. This is an ideal gas question again, so remember we need to convert this to metres cubed in a minute. So that's our original pressure and our volume. The moles of gas isn't changing, the gas constant is obviously a constant, and the temperature isn't changing. So our original pressure times by our original volume equals nRT. Our new pressure and our new volume is the same moles, the same gas constant, and the same temperature. So this enables us to make the following simplification. The first pressure times by the first volume equals the second pressure times by the second volume, because the nRT is the same in each case. So our original pressure times by our original volume, 100 kilopascals or 100,000 pascals, times by 170 centimetres cubed, convert that to metres cubed by dividing by 10 to the 6, or times 10 to the minus 6, equals our new pressure times by our new volume. We're being asked to work out the new pressure, and the new volume is 0.5 decimeters cubed. Again, make sure you convert that to the same units, which is meters cubed. So 0.5 times 10 to the minus 3, because it's decimeters cubed here and centimeters cubed to begin with. So what is the new pressure? Pressure times by volume, first pressure times by first volume, divided by the new volume, will give us the new pressure. So that gives us a final answer of, plug that into your calculator, 34,000 pascals, or 34 kilopascals. Answer C. So that brings me to the end of the Paper 3 2017 multiple choice questions. Thanks for listening. If you're still unsure how to arrive to the correct answer, if you weren't too sure about my explanations, do drop a comment below and I'll do my best to get back to you. You should be able to check out the other videos as well for clarification on the other multiple choice questions from the other exam series. Otherwise, best of luck with your exams, and I hope they go well.